Hello, my name's Hannah Doran and I'm a first year PhD student in the Systems, Power and Energy Research Division in the School of Engineering at the University of Glasgow. And I've also got collaborations with CERC in East Kilbride. So today I'm here to discuss my PhD topic, which is the potential for a waste heat recovery system by harnessing the decay heat from the back end of the nuclear fuel cycle. So the nuclear power production process is currently seen as a low carbon resource, and it could actually be a vital baseload technology to replace fossil fuels in the not too distant future. However, the consequence of this power production is that a large quantity of radioactive waste accumulates at the back end of the fuel cycle. Radioactive waste management procedures which aim to safely contain and isolate the waste have always been a worldwide burden, and this is because current storage facilities continue to fill up, whilst new ones experience delays due to limited funding and inconsistencies in legal and regulatory frameworks. It is also quite difficult to standardise these procedures because different waste types exist of different volumes, and this waste also evolves with time. So the radionuclide blend that you would have prior to packaging will be completely different after a certain cooling period. So this PhD topic presents an opportunity for this nuclear waste at the back end. Specifically, can we utilise and recover the decay heat that is emitted from these waste packages, and can we turn it into something useful, especially when the waste sits idle for long periods of time in a storage facility? So what is this decay heat potential? Well, when the fuel is burnt inside a nuclear reactor, neutron-induced fission occurs, and the products that are produced from this fission also undergo natural radioactive decay, which will release a large quantity of decay heat. Now, this primarily depends on the radioactivity content of the fuel in becquerels and the associated burn-up in megawatt days per tons of heavy metal. Now, burn-up is a measure of the energy content due to fission per unit mass of fuel inside the reactor. So this is all dependent on many factors like the operating conditions inside the reactor, the type of reactor, and also the type of fuel. For example, you could burn natural uranium, or you could enrich the content of uranium-235, so the actual fissile content has increased, which will increase the number of fissions and hence increase the radioactivity content. So to give an idea on this decay heat potential and how it changes with time, the diagram on the right shows the radioactivity for spent fuel when it's come out the reactor and how it's affected after so many years after processing. So initially we've got quite a high radioactivity content, and then after 100 years this has dropped by approximately 2 orders of magnitude, and then it will continue to decrease until 100,000 years, at which point the radioactivity is actually at the same level that it was when it was mined at the front end from the uranium ore. Now that's quite interesting because it proves that there's always been a problem with this radioactive waste and managing it. We need to get that radioactivity content down, we need to get the temperature down, but the time it takes to do this is very long, and but that also presents an opportunity if we can extract this decay heat and turn it into something useful. So countries can adopt different fuel cycles as well, which will heavily influence the waste streams and the different types of waste that exist. They could adopt an open loop cycle where the spent fuel just comes straight out the reactor into a cooling pond and then sent for interim storage and long-term disposal stages. Or you could adopt a closed loop cycle where reprocessing takes place. So it basically reprocesses 97% of this spent fuel and reuses it again in the reactor operation. So you'll have different waste streams that are produced depending on what fuel cycle you adopt. However, one thing is clear. The key areas of focus for this decay heat potential is going to be in the interim storage and long-term disposal stages, because this is where the waste is going to sit idle for long periods of time. And it's probably the most efficient place where we can recover this heat that's being emitted from the waste packages. So for these two stages, we need to assess the temperature in these environments. So delta T, temperature of the source, temperature of the surface, key post-irradiation time, so how long it's been outside the reactor for, how long it's been cooling for, and then finally the energy content in these environments, the burn up, and hence the decay heat output produced from each waste package. And I'm also interested in high heat producing waste, so I'll be looking at spent fuel, high level waste, and intermediate level waste as well. So let's have a look at these two stages in a bit more detail. So in the interim storage period, you usually have spent fuel that gets placed in a cooling pond for 3 to 5 years, and then that can be transferred to wet or dry storage facilities. For wet storage, we've got a cooling pond where the water acts as an efficient shield against radiation. Decay heat can be removed from the pond by a combination of active and passive safety systems. So this could be a ventilation system where the water is evaporated from the pool, or we can use recirculation where the water goes through the cooling towers, or we can add makeup water into the pond, which will maintain the level and temperature of the pond to prevent boiling. In dry stores, you can emplace the waste in a vault, a cask, or a silo. These are more favoured than wet stores because they have a passive safety system reliance, which usually requires less complicated monitoring. So the decay heat will be removed here through natural or forced convection currents, and the decay heat will be transported out up a chimney stack into the external environment. So then we move on to long-term disposal. There are two main ways you can dispose of it. It can be above ground or near surface, where the option for waste retrieval is possible. However, for the high heat producing wastes like spent fuel and high level waste, we really want this to be isolated from the environment. So we need to dig deeper and we need to go underground 200 to 1,000 meters below the surface, and we need to emplace the waste in a geological repository. Now there's a multi-barrier system approach that's adopted for each waste. You've got the waste form, you've got the waste package, and then a layer of backfill or seal, and finally a host rock. Now these layers are to ensure the disposal's stability and also to prevent radionuclide leakage into the groundwater and hence to the surface. So this method is the most feasible method for long-term disposal, but a lot of countries still haven't found a suitable site location for this, and there's also a lot of political and social opposition. So there's still quite a long way to go with this. So how are we going to calculate the decay heat? Well, as I said before, products that contribute to the decay heat, and one of them is called fission products, and they're produced from the thermal induced fission of uranium-235. So we can look at the uranium-235 fission yield curve here. It's just a probability distribution curve on all the fission products that are produced from this thermal fission. And it's dependent on the fission yield and the fission product's mass number. So these fission products have various half-lives. We have short-lived ones, long-lived ones. Just to give you some examples, we've got molybdenum 99, which is here, and iodine 133 for short-lived. And then for long-lived, strontium 90 and cesium 137 are also important that contribute to the decay heat. So once we've got information on the fission products that exist, we want to take their mean decay energies due to alpha, beta, and gamma emissions. And then we want to multiply these energies by the fission product's activity and then perform an energy summation. So if we've done that multiplication for each fission product, we then want to do a summation for all the fission products to get this decay heat output. Now, that will be for a fixed irradiation time inside the reactor, but then we want to model it for given post-irradiation times. So, for example, in the interim storage period, we're looking at between 30 years and maybe even 50 years. For the long-term disposal, this will be 100 years to tens of thousands of years. So really long time scales here. Now, the reason I want this decay heat and how it changes with this time, I want that to be fed into a waste heat recovery model where the spent fuel or the waste package acts as an anthropogenic source. And this will be in an external environment. It could be a cooling pond, it could be a dry storage facility, or a geological repository. So we need to have an idea of what these values are for those times. So here's the different environments, and we need some certain criteria on the technology we want to apply for waste heat recovery. So for a cooling pond, under normal operating conditions, we want the temperature of the water to be less than 60 degrees. Ideally, we want it to be at room temperature between 20 and 30 degrees. And then obviously, yeah, we've got water as the environment, so we might be looking at things like heat exchangers, heat pumps, thermodynamic cycles, etc. But what is important is that we have a secondary loop in place, because there could be some radioactivity inside the water. We don't want that going into our recovery technology. We want a secondary loop to pass that on to. So again, dry storage facility, the temperatures are quite varied depending on what type of waste store it is. So the outside room temperature between 20 and 30 for low level and intermediate level. High level waste, the outside temperature is a bit higher, 100 and 150 degrees. Now we've got the air to consider, so we might want to make use of the ventilation systems that are in place and recover the heat in that way. And we don't want the technology to be right on the waste drum, because we want to minimize degradation issues. So we want it to be at a distance, preferably at the outlet point, which is near the stack. And then finally, a geological repository. Temperatures will vary on the geological environment, but this is just a criteria for the multi-barrier system. So the waste package should not exceed 100 degrees on the surface. But obviously this temperature will be different if we have the systems stacked up in a certain area, because these repositories cover quite a wide area. And yet we've now got a geological environment, so we need to take into consideration things like active faults. We don't want anything to enhance leakage, fast groundwater movement to the surface, so we want that minimized as possible. And yeah, as I said, yeah, we want to minimize this leakage So if we maybe did some drilling, drilled down near to the repository, how is that going to affect the possibility of radionuclide leakage into the external environment? Okay, yeah, thank you. That's me done. Any questions?